that for many observations, we realize that in nature, the rate of change is proportional to the size. If you're talking about growth of a population, turn out that the bigger the population, the quicker the rate of change if you compare it to smaller population. So it's not just a proportional to, the rate of change won't be the same if you have, let's say, a population of 1,000 people and a population of 100,000. Or if you put, let's say, lab mice and put 1,000, give them all the food and everything they need, and put compare it to 100, turn out that the rate of growth of the 1,000 will exceed the rate of growth of the 100, not the growth itself. I mean, it's tend to reason that if you put 100 and you put 1,000 mice, you'll have more mice from the 1,000. I'm talking about the rate of change, the proportional to the population. So this leads to the following. Observation of natural growth and decay, for that matter, led to the conclusion that at times, not all the time, but at times, the rate of change, we're talking about growth in particular, is proportional to the size of the population, or the population size. So if we write, if the rate of change is the derivative, then we have f prime. This is the symbol, this alpha is a symbol to proportion. And if something is proportional, we can replace the proportionality symbol to say that the rate is a constant times the population. So f prime equals to some k constant times the population itself. Okay. If we let, suppose P of t is a population function, then we can write that P prime of t, the derivative, equals k P of t, or if we substitute P prime with dp dt using Leibniz notation, you can say that dp dt equals k p, like so. Okay? And this leads us to something we call the law of natural growth. So basically it's the same thing, but we're going to write, instead of P or F, we're going to say Y, and we're going to say dy dt equals some constant times Y, and the constant, if we have growth, then the constant is positive. Same thing, we can say that the law of natural decay, it will be the same thing, except we'll assign a negative value for k, And that will be the next line item, the law of natural decay we're going to say that the rate dy dt still equal ky, but k, the constant, will be negative. Does this start looking to be familiar to you? Okay. I can write it in terms of k. I can write, because of this relation, k will be dy dt divided by y, or we can say that equivalent statement will be the following. We can say that k equals dy dt times 1 over y, if we want to solve for k, or k equals y1 over y. Okay? Again, if k is positive, then we have something that's called RGR. If k is positive, then we have relative growth rate, RGR, where we're going to say that RGR equal, in this case, k, or y prime over y greater than 0. And likewise, we have RDR. If you guess that RDR stands for relative decay rate, you are absolutely correct. And here RDR is still going to be equals k, still going to be y prime over y, except it's negative. Okay? So you have these two terms. And here comes a very important theorem in calculus that has to do with exponential growth and decay. And actually, this theorem used extensively in differential equation. And the theorem states the following. The only solution, wait a second, before I go to the theorem, every equation that has a function in its derivative in the same equation called differential equation. I think I already mentioned that before. We've seen differential equations before. Remember, we have y double prime equals negative y when we have harmonic motion. That's a differential equation. This is also a differential equation because you can see that y prime, right here, you can see y prime equals ky. You have one equation where both derivative and function appear. So, the theorem said the following, that the only solution to the differential equation y prime equals ky, which is the same as what you see here in the RDR and RGR, okay, is given by y of t equals a constant c e to the power of kt. And you should recognize this expression in the box. A little modification will reveal the following. Again, this is something you should already know, but if I let t equal 0, okay, and we're going to let y of when t equals 0 equals c e to the k times 0, and e to the 0, of course, is 1, so it's equal to c, and we call this constant y sub 0. This will be the initial quantity. Okay, so y sub 0 will define as the initial quantity. And the solution to the differential equation is y of t now equals y sub 0 e to the k t. Okay? Which in algebra, college algebra and pre-calculus, we call this form as the exponential growth. Okay? Or if you remember something called PAT and PERT model, if you substitute y with p and k with r as the rate, then you have p equal p sub 0 e to the rt, or p equals PERT. Compare it to the annual growth PAT, p equal p sub 0 a to the power of t. Okay? So this is the result of the natural growth or decay, depend if k is positive or k is negative. Here's the statement I made before. Suppose y of t as a function represent a population then we'll call it p of t. Then we have the following: p of t equals p sub 0 e to the power of kt. More familiar form. Again, which is the PERT model. If R replaces K. Is the rate. Okay. All right, and now we are ready for some exercises.